Hey there, and welcome. Have you ever really thought about the science behind, say, your morning coffee, or the air you're breathing right now, or even the metal in a trumpet? Well, you're literally surrounded by an invisible world of chemistry. And today, we are pulling back the curtain on one of its most important ideas, solutions.
So let's just jump right in with a little riddle. What do you think a solid chunk of brass, a can of soda, and the blood running through your veins could possibly have in common? I mean, they seem totally different, right? But chemically speaking, they're all hiding the same secret identity.
Yep, that's the big reveal. They are all solutions. And by the end of this, you're going to know exactly what that means. And, more importantly, why it matters so much in our day-to-day lives.
All right, so what is a solution really? If all those different things can be one, what's the basic recipe? What are the ingredients we need to make one? Let's break it down.
You know, it's actually pretty simple. A solution is just a homogeneous mixture, which is a fancy way of saying it's a smooth mix that's the same all the way through. It's got two main parts, the solute, which is the stuff that gets dissolved, and the solvent, which is the stuff that does the dissolving. Just think about making salt water. Salt is your solute, water is your solvent. Boom, you've got a solution. Now this is where things get really interesting, because most of us just think of solutions as liquids, right? Well, that's a total myth. Solutions can be gases, liquids, or even solids. The very air we're breathing, it's a gaseous solution of oxygen dissolved in nitrogen. And that brass trumpet we mentioned? That's a solid solution of zinc dissolved in copper. Wild, huh?
Okay, but it's not enough to just throw things together. In the world of solutions, the exact amount of each ingredient, what scientists call concentration, is absolutely critical. And I mean, it can literally be a matter of life and death.
And this is really the core idea here. The usefulness of a solution, how important it is, all comes down to its composition. Getting that mix just right is everything. Let me show you a really powerful example of this.
So our drinking water often has a tiny amount of fluoride in it to protect our teeth. At a concentration of just 1 part per million, which is like one single drop of water in a massive swimming pool, it's incredibly good at providing cavities. A tiny amount, a huge benefit.
But get this, if you increase that concentration by just half a part per million to 1.5 ppm, that good thing suddenly turns harmful. It causes a condition that mottles the teeth. It just goes to show you how incredibly fine that line between helpful and harmful can be.
And to get that precision, scientists have a few different ways to measure concentration. You might see mass percentage on a bottle of bleach, or a volume percentage for the antifreeze in your car. And of course, parts per million when we're talking about those super tiny amounts of something, like pollutants.
So, we know that how much you add is key, but what makes something dissolve in the first place? You know, why does salt just vanish in water, but oil sits right on top? Well, it's not random. It's all governed by some basic rules of chemistry, rules of attraction and pressure. The first rule is super simple, and it's a golden rule in chemistry. Like dissolves like. It just means that polar things, like salt, which have little positive and negative charges, love to dissolve in other polar things, like water. And nonpolar stuff, like oil and grease, well, they dissolve best in other nonpolar stuff. Simple as that.
Now for pressure. This is where things get fizzy. There's something called Henry's Law, which basically says that if you crank up the pressure of a gas sitting on top of a liquid, you can force more of that gas to dissolve into it. This is exactly how they get the bubbles into your soda. They seal that can under super high pressure.
But that same law, Henry's Law, has a really dangerous side. It's the reason scuba divers have to be so careful. See, when a diver goes deep, the intense pressure forces extra nitrogen from their air tank to dissolve into their blood. Now, if they come up to the surface too fast, that pressure drops suddenly, and all that nitrogen comes fizzing out of their blood, just like the carbonation in a soda can, creating these tiny, painful, and dangerous bubbles. It's a condition called the bends.
So, how do you solve a problem like that? Well, you change the solution itself. For really deep dives, divers breathe a special gas mixture where some of that nitrogen is replaced with helium, which doesn't dissolve in our blood nearly as easily. It's a brilliant, life-saving chemistry hack.
Okay, so we've seen how solutions form, but what happens after they're mixed? This is where it gets really cool. A solution isn't just its parts added together, it actually develops brand new properties, almost like superpowers.
These are called colligative properties. And here is the craziest part, the key thing to remember. These properties don't care what the solute is. It could be salt, could be sugar, doesn't matter.
All that matters is how many particles of the stuff you've added. It is all about quantity over quality. So, it all starts with something called vapor pressure. Imagine the surface of a liquid is like an exit door at a party. In a pure liquid, molecules can leave easily. But when you add a solute, those new particles are like extra people crowding the doorway. They get in the way, and fewer of the original molecules can escape. That lowers the vapor pressure. And because of that one change, two other things happen. The boiling point goes up, and the freezing point goes down.
And we totally use this superpower all the time. Antifreeze is the perfect example. By adding ethylene glycol to the water in your car's radiator, you create a solution that won't freeze until it gets way, way colder, down to minus 17.6 Celsius. It's a perfect way to protect your engine block in the winter.
Okay, last superpower, osmosis. You can think of it as nature's way of trying to balance things out. If you have two solutions with different concentrations and you separate them with a special filter, the solvent, usually water, will automatically move from the weaker solution into the stronger one, trying to even out the mixture.
This process is unbelievably important inside our bodies. Our red blood cells are basically tiny little bags of solution. If you put them in a fluid that's too salty, water rushes out of the cells and they shrivel up. If you put them in a fluid that's not salty enough, water rushes in and they can swell up and even burst. This is exactly why medical IV drips have to be isotonic, meaning they have the exact same 0.9% salt concentration as our own blood.
Wow. Okay, we have covered a ton of ground, huh? From fizzy soda to antifreeze to the IV bags that save lives. So let's just pull it all together and talk about why understanding all this stuff really matters. So, what are the big things to take away? Well, first, solutions are literally everywhere. They're the foundation of metal alloys, life-saving medicines, and life itself. Second, concentration isn't just a number. It's a critical measure that can be the difference between something being helpful or harmful. Third, simple laws of pressure explain all kinds of things we see, from our soda cans to scuba safety. And finally, by mixing things, we create totally new properties that we can use to our advantage every single day.
You know, once you start looking for it, you'll see the science everywhere, from why sugar dissolves faster in your hot tea to why we salt the roads to melt ice in the winter. Now that you know the rules of the mix, the next time you see something dissolve, or mix, or fizz, you'll know the science behind the magic. So what other everyday mysteries are you going to solve?